Alright, welcome to section 10.6, Exponential and Logarithmic Equations and Applications, except we're only covering objectives 1 and 2, which means we're just covering exponential equations and logarithmic equations. Alright, so some properties for solving exponential and logarithmic equations. So, for all real numbers, where b is greater than 0 and b is not equal to 1, and any real number, x and y, then we have the following. First, if x equals y, then b to the x power must equal b to the y power. We've seen that if the bases are the same, you can equate the exponents. Secondly, if b to the x power equals b to the y power, then x equals y. So it is similar to the top one. We can assume if we're given the first one, the second one is true, and then the other way, if we're given the second one, then the first one must be true. Because sometimes you can't go back and forth between two things. Sometimes it only works one way. But in this case, it works either way. If you're given this first one, you can assume the second, and then if you're given the second one, you can assume the first. Kind of neat. And then third, if x equals y, and x is greater than 0 and y is greater than 0, then log base b of x must equal log base b of y. Okay, so once again, if x equals y, then we can assume that log of b and x and log b of y are the same as well. And lastly, the reverse of the third one. If x is greater than 0 and y is greater than 0, and log base b of x equals log base b of y, then we can assume the other way, then x equals y. So once again, same concept. When we have the first one, we're allowed to assume the second one. And then if we have the second one, we're allowed to assume the first one. It doesn't always work this way in mathematics. Sometimes you can assume one follows, but then it can't go backwards. Alright, so let's take a look at solving. So I like to break up solving into type 1 and type 2. So for exponential, I think of a type 1 equation and then I think of a type 2 equation. And I'll tell you how I tell them apart. First off, a type 1 equation is when you can match the bases. These ones are usually simpler. So let's take a look at example 1. Can we match the bases? First off though, is this exponential? It is. How do I know? Well, the exponents are in the variables. Okay, so it's exponential, and then I ask myself, is it a type 1 or type 2? Well, if I can match the base, it's a type 1. So let's see. 3 and 9. You know what? I can make 9 look like 3. So 3 to the x power is going to equal, and then 9 I can rewrite as 3 squared. And that's to the x plus 4. And then using the power rule, multiply these out. 3x equals 3 to x plus 4. So the bases are the same, so I can assume that the exponents are equal to each other. So we'll go ahead and write that down. X equals 2x plus 4. And then solving. Multiply this out. We get x equals 2x plus 8. Subtract x from both sides. And then let's keep writing over here with my arrow. So negative x equals 8. We've almost solved. Let's go ahead and divide both sides by negative 1. And we get x equals 8. We don't need to check these because it came from an exponential. And the variable's in the exponent, so no restrictions there. Okay, so this one was easier as a type 1. Why was it a type 1? Because we could match the base. Let's take a look at the next one, which is I consider a type 2 equation. Now what happens in a type 2 equation? This is when you cannot match the base. So what is the plan if you can't match the base? You're going to go to log form. If things aren't working in exponential form, you move to log form. So let's take a look at this problem here. Is it exponential, first off? Well, it is. The variable's in the exponent. Awesome. Can we match the bases? That's a base 5 and that's a base 9. I can't think of any way to manipulate 5 and 9 to look like exponent versions of each other. So because of that, I can't work in exponential form. I'm going to move to log form. So this is where we're going to log both sides. And this is also where you have to choose either base e or base 10. So you can use natural log or common log. 1 or 2. Which one should you use? It doesn't matter. Unless for some reason you see an e in this problem or you see a 10. If you see a 10, I would use base 10 because they can cancel. And if you see an e, I would use natural log. I don't see either one, so I'm just going to choose natural log because it's shorter and easier to write. Great reasons. Okay, so let's go ahead and log both sides. Natural log 5 negative x plus 7 equals natural log of 9. Once again, in your work, please make sure to show writing log on both sides. Don't do any canceling in your head. Write on the paper, logging both sides, please. Please and thank you. All right, so, and then what are we going to do? Well, my variable is up in the exponent. I have a hard time solving when it's up there. Do I know of any way to bring an exponent down to the normal, and I'm going to call this the baseline? Any way to do that? Well, if you recall, log base b of x to the r, I can bring that exponent in the front, which is r log base b of x. So let's go ahead and use that rule. And sort of a joke I like to use when I talk about these is you can think of your exponent as the apple in the tree. If you're desperate to get at that apple way up at the top, you could always just log the tree down to bring the apple down. Kind of a sad reason, but I think it's a good way for me to remember. So we have negative x plus 7, natural log of 5 equals natural log of 9. So now, how do we get x by itself? Well, we can go ahead and divide both sides by the natural log of 5. And then we have x plus 7 equals natural log of 9 over natural log of 5. We've almost solved for x. Let's go ahead and subtract both sides by 7. And we get x equals the natural log of 9 over ln 5 minus 7. Now, sorry about the geese in the background. Some professors would like you to actually subtract these two fractions together. I'm not going to be too picky about this, but if you wanted to, you could just go ahead and build up the bases. So then that means x would equal natural log of 7 minus 7 ln 5 over ln 5. So these two are considered equivalent ways of writing your answer. Now, please do not use a decimal approximation for these. We're not using calculators for logarithms in this class. Okay, so no calculators for this. Please just leave it in the nice ln format. Alright, so let's take a look at the logarithmics. So once again, I have a type 1 and a type 2 for logarithms. Alright, so how can we determine a type 1 equation? Well, that's if both are logs. Or you could extend this to all terms are logarithms. If they're all logarithms, then we're going to go ahead and use the rule log base b of x equals log base b of y, and assume that the arguments must equal each other. That's what we're going to do. That's the plan. So let's see. Are these, first off, is this a logarithmic equation? It is. They're both logarithms. Next, is everything in the equation only a logarithm? And that answer is yes. So because they're both logarithms, I'm going to use the rule that if I have two logs that have the same base or equal to each other, then we can just equate the arguments. So let's see. Well, they have the same base, which means I can go ahead and just equate the arguments. So let's go ahead and do that. So 3x plus 5 must equal x minus 6. That's the rule we were given up above here. So let's see. Let's go ahead and solve. Minus x, minus 5, minus 5. So we have 2x equals negative 11. Dividing both sides by 2, we get x equals negative 11 over 2. So I'd be tempted to say we're done, but recall, for logarithms, do we have any restrictions? Well, the arguments cannot be negative. Just in general in life, try and remember, arguments shouldn't be negative. They should be constructive and then solve problems, not just be negative. Okay. You know what? If I plug negative 11 over 2 into this argument, I'm going to get a negative number. That's a negative 11 over 2 minus 6. That's already a negative number. Now, it doesn't matter if it only makes one argument negative, it doesn't work. Even if it works for one, which it would probably work for this. Because it makes one argument negative, there's no solution. So I'm going to write no solution. Makes argument negative. Okay, so once again, provide the answer and then provide your reason for saying there is no solution. I do look for both of those things. All right. Okay, well that was pretty easy. When you have only two logs, it's pretty simple. Just go ahead and equate the arguments. So now let's take a look at the type 2. Well, the type 2 is you have something that's not a log. Is not a logarithm. Now, what do we do with that? Well, if it's not a logarithm, we have some trouble solving it, so we're going to turn it into exponential form. So if you'll notice, with the type 2 equations for log and exponents, for the log type 2, we change to exponential form. For the exponential type 2, we're running into problem solving exponentially, so we change to solving in log form. So once again, that's how it's nice that they're intertwined. We can just change between them if we're running into problems. So let's go ahead and do that. First off, is this a logarithmic equation? It is, because there's a log in it. All right. But is it a log type 1 or 2? Well, notice we have that 3 hanging out on the other side. That is not considered a logarithm. So because of that, we're going to go ahead and solve using the type 2 method, which means to change to exponential. And we know how to do that. The base raised to the answer equals the exponent. So changing to logarithm or to exponential form, 5 to the third power equals 3x plus 2. And what do you know? Now the x is outside of our argument. It's a lot easier to solve for. Before it was inside our argument, and I didn't know how to split that up to solve it. So now it's in the nice format. We change from logarithm to exponential. Let's go ahead and solve. So 5 cubed is 125 minus 2 equals 3x. 125 minus 2 is 123. 3x, and then let's see, divide both sides by 3. Now let's see, can 123 be divided by 3? Well, if we add up all the digits of 123, that's 1 plus 2 is 3, plus 3 is 6. Could 3 divide 6? Yes, so I know this must be divisible by 3. This was just a weird little shortcut way of seeing if things are divisible by 3. You don't need to know that. But we know it's divisible by 3. And we can go ahead, use our calculator, 123 divided by 3 is 41. Once again, though, careful. Can we just box our answer? No, because this is with logarithms. And the x comes from our argument. Does it make our argument positive or negative? Now, it makes it positive. But because I'm not writing no solution and then writing out my reason, if you write out your reason, you don't need to show your work. But if you don't write out a reason, you need to show your work. Okay, so once again though, if you write no solution, you need to write it makes your argument negative, or you have the reason. In this case, let's go ahead and check. 3x plus 2, 3 times 41 plus 2. 3 times 41 is 123 plus 2, so 123 is 125. This is it's positive. So it checks out. So because of that, we'll go ahead and box our answer. So once again, this is just the way to show your work for logarithms. Check your work to see if it makes it positive or negative. If it's positive, you can just box your answer and show your checked work. If by just looking at the problem you know it makes one of them negative, you can just go ahead, write no solution, and makes argument negative. And if you want to, include an arrow showing to your argument. Alright, so now let's just take a look at some other problems and determine which kind they are. So, example 5. Well, it's logarithmic, okay? So I know we're working with a logarithm. The question is, am I working with logarithm type 1 or type 2? What do you think? Well, there are 3 log terms, which we haven't really seen yet, but all of them are logarithms. So all are logs, which means this is the type 1. My goal then would be to make log base b of a equal to log base b of x and then equate the arguments. That's my goal. How do we do that? Because right now I have a log on one side, but I have 2 on the other. You know what? I know rules for condensing logs. That was something we practiced a section or 2 back. I can condense them. See that subtraction sign? I can rewrite this as log of 8 of 2x plus 5 divided by 3. And now, what do you know? I have 2 logs equal to each other. Because of that, I can go ahead and equate the arguments. So, 2x plus 5 divided by 3 must equal 2. And now I can go ahead and keep solving. So using some cross multiplication, that's a 2 over 1. We get 2x plus 5 equals 6. And solving further, subtract 5. 2x equals 1, divide by 2, divide by 2. X equals a half, or 0.5. Let's see. Once again, this is a logarithm. We have to check that it doesn't make any of our arguments negative. Well, this one right here, there's no x in there, no x in there. There is an x in this one. So let's go ahead and check. 2 times a half plus 5. 2 times a half is 1, plus 5 is 6. Okay, so that's positive. It works out. Our answer is good. Okay, let's take a look at the last example. Okay, is this exponential or logarithmic? It's logarithmic. How do I know that? Well, there are logs in it. The next question, is it a type 1 or a type 2? It's a type 2. How do I know that? Well, one of the terms is not a log. There's a little alien hanging out. Okay, so since this is the type 2, my goal is to go from log base b of x equal to y form to exponential form. So by equals x. So we're going to try to go to exponential form. But it's not in this perfect format yet. I need one log on one side equal to a number. And right now I have 2 logs equal to a number. How do I condense those 2 logs into 1? Well, once again, if you recall, we have some of those rules with logs. If there's an addition sign and the logs are the same, we can keep the log and multiply the arguments. And this is where that handiness of playing around with logs comes in handy. Okay, so now I have 1 log equal to a number. Let's go ahead and change to exponential form. That's the plan we have for type 2 logs. What's the base here, though? The base is 10. Remember, if you don't see the base, it's 10. So 10 raised to the 2nd power must equal your argument. Okay, so that's going to be 100 equals x squared minus 21x. We distributed. And then let's see. Ooh, it looks like we have a quadratic coming up. So minus 100 from both sides. We have a quadratic equation because we have that x squared. Okay, so let's see. Minus 21x minus the 100. Can we factor this? Let's see. Factors of 100, that when I subtract them, I get negative 21. So factors of 100. Well, the first one I can think of is 4 and 25, right? Because 4 quarters is 100. And if I subtract those, if I have a positive 4 and a negative 25, I'll get the negative 21. All right, let's go ahead and do that. So that's going to be x minus 25, x plus 4. Once again, if you need any help with factoring or any resources, please send me an email and I'll go ahead and send them to you, or just come by an office hour and we can work on that. Okay, so I factored them. Let's go ahead and set each term to 0 to solve. Add 25, and then add 25. X equals 25. Can't box that yet. Minus 4, minus 4. X equals negative 4. So we have a positive 25 and a negative 4. Do they both work? Well, let's see. I'm going to go ahead, since we have 2, let's write them out both for checking. So let's check negative 4. So we have 2 arguments that have a variable, the x and the x minus 21. So x, if I plug in 4, that's going to equal negative 4, which is already negative. So this is a no. So the 4 already doesn't work with just one of the arguments, which means it doesn't work. Even if it works for one and not for the other, As long as it doesn't work for one, it will not work. Okay, so extraneous makes argument negative. This is extraneous. Now, why didn't I write no solution? Well, we don't know if there's no solution yet because there's still one other possibility. If they both didn't work, then we would write no solution. But at the moment, since only one works, only one doesn't work, it's called extraneous for now. Let's go ahead and check 25. Well, when I check x for 25, which is the one argument here, that works. That's equal to 25. It's a positive number. Let's check the next one, x minus 21. That's going to be 25 minus 21, which is going to be positive 4, which also checks out. So it works for both, so this is going to be a solution. And because of that, we're going to keep the statement extraneous for the other one. If they both didn't work, that's when we'd write no solution. But since only this one doesn't work, we'll call it extraneous, and then state why. It makes the argument negative. Alright, that is it for this section. If you have any questions, once again, stop by my office hour or send me an email and we can set up a time to meet.